explained density, pressure, and total force. We shall now investigate the property of liquids, which makes possible all hydraulic mechanisms and machines. Let us take a glass tube of uniform cross-section and containing a close-fitting piston at one end. Now let us place another close-fitting piston in the other end of the tube, so that the water is flush with both pistons, and so that there is no air between the pistons. The pistons, as you can see, are free to move in the tube. Now let us anchor the tube in a steady position, mark on a card the position of the pistons in the tube, and apply an equal force on each piston. Notice that as this force is applied, there is no motion of the pistons, despite the fact that they are free to move. This is because the liquid between the pistons cannot be compressed. Although considerable force is applied, the pistons do not move from their marked positions. If we apply more force, we find that the pistons will still not move until some liquid is let out of the tube, which can, in this case, only happen when the tube breaks. Thus we see demonstrated a most important property of liquids, namely that they are virtually non-compressible. It is because liquids cannot be compressed that they are so useful for doing work in hydraulic systems and machines, and can be used to transmit force. In our glass tube fitted with pistons, we were applying force to a liquid which was thoroughly confined. Let us examine now the effect of a force applied to a confined liquid. As an illustration, let us take two containers, one fitted closely with a cylinder of hard wood and the other containing water. If we apply force to the top of the block of wood, as a simple illustration, let's pound the block with a hammer. We find that this force will be transmitted to the bottom of the container. And eventually, as we continue to hammer, the bottom will be forced out. The sides of the container remain substantially the same. This indicates that the force applied to the top of the block of wood is transmitted to the bottom and does not appreciably affect the sides of the container. Let us now apply a similar force to the container of water. Obviously, we cannot hammer water, so to enable us to apply force to the liquid, we place in the top of the container a close-fitting piston, which is flush with the surface of the water. As we apply a force to the piston, we find that not only does the bottom begin to bulge, as in the case of the wood, but that the sides of the container begin to expand also. This indicates that with the water, the force is transmitted to all portions of the containing vessel and not to the bottom alone. It is possible to demonstrate this in another way, and at the same time to measure the effect of the force applied to the confined liquid. Let us take a bottle, in the neck of which is placed a close-fitting piston. The piston is free to move, lies directly on the top surface of the liquid, and the liquid is totally confined. Let us place a weight, say of 50 pounds, so that it acts on the piston, whose area of cross-section is 1 square inch. After the weight is applied, let's drill a hole in the side of the container. We note that water gushes out through the hole. A force is necessary to drive the water out, and its gushing through the opening indicates that before the hole was drilled, the water was pushing against the side of the container with a certain amount of force and pressure. We can measure this pressure if we insert a pressure gauge in the hole, so that the liquid being forced out now acts on the pressure gauge. When we insert the gauge, we find that the pressure on the side of the container is 50 pounds per square inch. In this demonstration, and in those to follow, we have neglected the weight of the water in the container, which is very small compared to the 50-pound weight acting on the liquid. But the pressure on the container is the force of 50 pounds divided by the area on which it acts, which in this case is the 1 square inch area of the piston. In other words, the pressure acting on the confined liquid is 50 pounds per square inch, which is the same pressure as that exerted on the side of the container, as measured by the gauge. That this is true for all portions of the containing wall can be demonstrated by inserting a gauge anywhere in the container. We find when we do this, it reads the same everywhere. And so we see that the pressure acting on a confined liquid is transmitted to all portions of the wall of the container without the pressure becoming less great. Where the pressure acting on the confined liquid is 50 pounds per square inch, the pressure on all parts of the container is 50 pounds per square inch. This principle holds good for any pressure which will not burst the container. If we were, in this simple hydraulic system, to apply a pressure of 20 pounds per square inch to the liquid, we would find that a gauge inserted in the system would read 20 pounds per square inch pressure. The same would hold true for a 100-pound weight, and so on. Actually, a simple hydraulic system operating on these principles is used to calibrate gauges. While we are discussing the use of gauges to measure pressure, let us examine how these gauges work. The type of gauge most commonly used in hydraulic equipment operates on a principle that can be observed by attaching a short length of garden hose to a source of water under pressure. We note that before the water is turned on, the hose is at rest in a somewhat curled up position. As we turn on the water tap, water under pressure begins to flow through the hose and to force it to uncoil. If the pressure of the water flowing through the hose can be made sufficiently high, the hose will endeavor to straighten out completely. We can illustrate this principle in another way with a child's toy known as a snake or tickler. When air was blown through it, the air acted against the force of the spring to straighten out the tube of paper. As we ceased blowing and pressure was removed, the spring returned the tube of paper to its coiled position. If we can imagine this toy working under water instead of air pressure and operating in the same fashion, we have the principle of the gauge most commonly used in hydraulics. The Bourdon-type gauge. This gauge consists of a flexible coiled tube of light, elastic metal or other substance. The tube is closed at one end and open at the other, so that the liquid may flow into the open end of the tube. When there is no liquid flowing into the tube, it appears in something like the form shown here. The closed end of the tube is connected to a pivoted segment gear, and the segment gear is mounted to mesh with a small pinion gear. Mounted on the pinion is a pointer, and at the end of the pointer, a scale. As the gauge is connected to a hydraulic system so that liquid under pressure is forced into it, it tends to straighten the tube out. As it straightens, it pulls the segment gear, which moves against the pinion. And moves the pointer, which reads on the scale. The greater the pressure of the liquid entering the tube, the more it will straighten the tube out, and consequently the farther it will move the segment gear, the pinion, and the pointer. Thus, the amount which the tube moves is proportional to the pressure of the liquid being applied to it. Here is a phantom view of the operation of a Bourdon gauge. By By plugging this gauge into a system where known pressures can be applied to it, we are able to calibrate the scale of the gauge to give specific pressure readings. Another type of gauge measures pressure on a slightly different principle. It consists of a small cylinder containing a close-fitting piston. Above the piston is a piston rod, and fastened to the top of the piston rod, a small button. The cylinder is open so that a liquid under pressure may flow into the bottom of it. As the liquid enters the cylinder, it pushes up the piston rod, and the button on top of it. To counteract the pressure of the liquid, a small coiled spring is placed so that it pushes down on the piston rod and tends to oppose the pressure of the liquid. As the pressure of the liquid acting on the piston is increased, it will push harder, move the piston and piston rod upward, and consequently compress the spring a greater amount. A pointer is attached so that it can indicate the amount of compression of the spring on the scale. Since the distance that this spring is compressed is proportional to the pressure of the liquid, the scale can be calibrated to give direct pressure readings. This type of gauge, whose workings we have explained schematically, is known as a Schrader gauge. This gauge is calibrated in the same manner as was the Burden type gauge, by fitting it to a simple hydraulic system where known pressures can be applied to it, and marking the gauge to correspond with these known pressures. Let us return now to our example of the glass tube containing a confined liquid and closely fitted with two pistons, one at each end. As we saw before, these pistons are free to move. In other words, when a force is applied to one piston, it is transmitted through the liquid and acts on and moves the other pistons. We saw also that the liquid in the tube cannot be compressed. Consequently, the distance one piston moves will be exactly the same as the distance the other piston moves. In a system of this kind, we refer to the piston to which force is applied as the input or A piston, and that to which force is transmitted as the output or B piston. These principles of transmission of force through a confined liquid will hold true regardless of the shape of the container. Thus, if our glass tube is in the shape of a U, we will again find that a force applied to the input piston is transmitted through the liquid and moves the output piston. And again, if these pistons are the same size, the distance moved by one will be exactly the same as the distance moved by the other. The reason for this is that as we move the input or A piston down, a certain amount of liquid is displaced. This liquid cannot be compressed, but pushes the rest of the liquid in the tube so that an equal amount of liquid pushes the B piston up. The quantity of liquid displaced by the A piston is, as we can see, exactly the same as that which causes the B piston to move up. This principle, that the amount of liquid displaced by the input piston is exactly the same as that which causes the output piston to move up, is true regardless of the sizes of the input and output pistons. For example, here we have a tube fitted with two pistons, where the output piston has a considerably larger area than the input piston. The size of these pistons does not alter that as the A piston is moved downward, it displaces a certain amount of liquid, which pushes the liquid in the tube so that the B piston is moved upward by the same amount of liquid. When we say amount or quantity of liquid, What we are actually talking about is the volume of liquid displaced. Thus, we can see that the volume of liquid displaced by the input piston as it moves is the same as, or equal to, the liquid which pushes up the output piston and causes it to move. Therefore, as the size of the output piston increases, the distance it moves upward will be less. This can easily be seen if we think only of the amount of liquid which the input piston displaces and the amount transferred, which causes the output piston to move. These can be visualized as two cylindrical columns of liquid. It can readily be seen that while the volumes are the same, the column of liquid displaced by the input piston is longer than it is wide, whereas the column which moves the output piston upward is wider than it is long. Consequently, as the size or area of the output piston increases, the distance it moves will be less. We have demonstrated in this film that liquids are virtually non-compressible, and that pressure applied to a confined liquid is transmitted to all portions of the interior of the containing vessel. And further, that this pressure is transmitted in the same amount, or undiminished, to all portions of the container. These principles were discovered early in the 17th century by a French scientist named Blaise Pascal, and are summed up in a statement which is now a fundamental principle of all hydraulics. You would do well to memorize this statement, which is known as Pascal's law, and is stated as follows. Pressure exerted on a confined liquid is transmitted undiminished to all portions of the interior of the containing vessel.